this work that I'm going to present here today is related with a machine learning model that is based on Bayesian networks. There are several implementations of Bayesian networks nowadays, but some of them are not very scalable, and I'm going to talk a little bit about that, about the scalability and other things that are related with interaction with the user. And this work is a joint work with other people. At the moment, I have a PhD student that is working on the implementation of the scalable algorithms. And previously, I had some people working with me, Isilda Almeida, that was the first implementer of the system that we have called ExpertBayes. This was implemented in Java, but had some limitations in efficiency and scalability. Also, Thiago Vinhosa helped a lot with all the theory behind these the algorithms and everything that we needed to implement. Pedro Ferreira also helped with some stuff with the theory. Paulo Borges was a collaborator in a project that we had to develop a system for machine learning, self-autonomous data analysis system. Ana Sarabando was a nurse that helped building one of the networks that I'm going to show you here. And these two people from University of Wisconsin were responsible for the providing data and also for providing Bayesian network for the breast cancer domain that we have here in this presentation today. Okay, so some of this work is a bit old, some old things, but André is taking this work on, and he's be implementing and have a very efficient implementation currently for all of these things that I'm going to talk about today. Okay. So just to put a little bit of context, I don't know if everyone there is acquainted with Bayesian networks. So Bayesian networks are graphical models, basically directed acyclic graph, where nodes are random variables, and usually discrete, but not limited to, because we can work with continuous variable as well. And edges are conditional dependencies between the random variables. Each node is decorated with the conditional probability table, and the model can be built manually. I mean, there are several softwares actually that can allow the network to be built manually. I can draw the edges and the nodes and connect variables together, and but we can also learn the structure and the parameters for this model. The structure is the graph itself, the edges, direct edges and the nodes, and the parameters are the probability tables that are decorated for each node. Okay, so there are several algorithms that can do that, and I mean the literature is plenty of solutions for this problem. It's not a very easy problem because of especially because of the complexity. If you want to build a very general Bayesian network, you face a complexity problem. So this is an example of a very simple graph. And this is, I mean, didactic graph. Everyone uses this graph to show examples of Bayesian networks. I have here 3 random variables that can be observed: the weather, a sprinkler, and the lawn. And this network here says that the weather is influencing somehow the lawn and the sprinkler and the weather influence the lawn. So for each one of these nodes, we build a conditional probability table for weather. As weather doesn't have any parents in this graph, we can only build the probabilities for each one of the values that weather can take. Of course, each one of these random variables are observed and can take values, right? And these values can be measured. I mean, these measurements that I can have here in these tables can come from several different sources. It can come from experience. It can come from observation. It can come from the literature. So here we have a more complex table where we represent all the combinations of values of weather and sprinkler that influences the lawn. In the case that the lawn is wet or dry, we have all the combinations of weather and sprinkler, and for each one of them, I have a probability associated. So why do you need a conditional probability or Bayesian network? The Bayesian network is a way of taking a very huge amount of observations and factorizing these variables that are observed in subgroups that can be independent. And in that way, I can have a more summarized model. Instead of carrying my table of observations with every single observation that I have for the values of these variables, I can simply take the table. Suppose I have 1 million rows of observations with several variables. What I can do is to transform this million rows table in a factorized conditional probability table like this one here. I mean, I have several conditional probability tables according to the relations that I think that there are between these variables. I mean, this is not so simple as I'm explaining here, because the influence that I have here may not be causation, and especially when we build the structure automatically, the structure that arises usually are not causal, because they are computed in a way just counting and computing the conditional probabilities of a variable given its parents. So the final network that's built usually cannot be exactly considered to be causal links. I mean, all of these things here cannot be considered causal links, okay? But we can do a very decent work with these models. And this is quantitative part, and this, I mean, there are two good characteristics here for this model. One of them is that I can have quantitative values for the probabilities for each one of the values of these variables, and I can also have the relation between the variables. And this is something that's interpretable, and interpretability is something that's very important nowadays. So this is something that people like to see. I mean, the correlations or associations among the variables. So this is one of the characteristics that's very important in this model. So once we have this model built, that can be manually built or automatically built, we consist of a graph and the conditional probability tables. We can answer queries like, given that it rained, would the lawn be wet? This is trivial from these tables here, because if it's raining, the lawn is influenced by rainy and sprinkler, but if it's raining, the sprinkler doesn't have importance, because it's 100% either for a sprinkler on or for a sprinkler off. So this is easy to be calculated, but we can also calculate things using the Bayes theorem. Calculate things like, given that the lawn is wet, what would be the reason? The rain, it's rainy weather, or the sprinkler is on. For that example in particular, if you do all the calculations, you can find that it's because it's raining, okay? It's very rainy. So there are several softwares for Bayesian networks, for handling Bayesian networks. I enumerated some of them here. There are several of them. I put dots here because there are several of them. Each day, people appear with some things. I think the most complete one from what I know is this UNB-Bayes here that's being updated. Actually, it was updated March this year. This software was updated, and I think this is the most complete nowadays. This one is not continued. I mean, it's discontinued. And there are also these are all dedicated software to Bayesian networks, but there are softwares that are toolkits that implement Bayesian networks and other things like Weka or Orange and RapidBiner and all the other software. So there are a great variety of things that software that implement Bayesian networks, but as you see later, some of them are not very scalable and don't solve many problems, even medium-sized problems. So as I said, there are some limitations. Some of them are not batch interactive. In other words, what I mean is either they are dedicated to interaction with the user in a way that they can build my own network graphically, and I can drag and drop nodes and build my own network and then do inference. Or they implement something in batch, like for example, BNLearn that is implemented in R is language oriented, right? So I can program using BNLearn in order to do batch learning and batch testing, right? But not all of these software is very, very user friendly, and they don't allow people, the experts, to remove nodes, insert edges, or remove edges. And once the model is done, try with several different structures. They are not scalable, and I'm going to see you some testing here, actually some preliminary testing, because this needs to be further experienced. And some of them have even testing limitations, like for example, BNLearn R. When you train a model in BNLearn, you can only test something if your batch test has all of the categories, classes that you use it to train. If you train for 3 classes and you give a test set with just 2 classes, BNLearn cannot do the testing for you. So this is, I understand that this is a limitation just because they wanted to build networks and do training and testing for performance. But for the end user, this is not convenient, right? So, so I'm going to talk about 2 things. One is handling interactions and manually built networks, and then I'm going to talk about the ExpertBayes. That was the first software that we implemented. And I'm going to show you ExpertBayes in 3 different data sets: prostate cancer, breast cancer #1, and breast cancer #2. These are 2 different tasks, machine learning tasks in breast cancer. And the second part will be related with handling scalability, showing some in-progress work for the high-performance ExpertBayes that we have been implementing. Actually, Andrea is the one that is implementing all the codes. So ExpertBayes is an interactive front-end and back-end. It's not scalable, but implements several functionalities and allows interaction with the user. Unfortunately, I don't have here the software in this machine. I had the software implemented running in another Windows machine. In this machine that I am presenting here today, I don't have Java running, so I cannot demonstrate the software to you. But I can give you, if you send me an email later, I can give you a link where you can try the software ExpertBayes and the HPExpertBayes, both versions, if you are interested. So I'm sorry about this slide. I just put it here because the main algorithm implemented by ExpertBayes is very simple in a way that the idea of ExpertBayes when we designed it was to be friendly to the user. The user could put their model, and this the motivation came from me and the other people working with experts from the medical area, medical experts, and these people didn't have a way of interacting with the models that they were building. They built models and they published the models and they calculated probabilities in Excel. That's how I saw them doing things. They didn't know how to interact with the software that was available at the moment for Bayesian networks. So we decided to implement something very simple with a graphical interface where you can load or you can draw your own network. And then the idea was to do very small changes to the original network built by the experts in order to find better models, in order of accuracy and maximization of log likelihoods. That is, there's several metrics that you can use to know if your Bayesian model is working well for the data. So we implemented the train tests and all of cross-validation and everything in the system. And the algorithm is very simple. We read an original network, and then we read train and test sets in order to populate and build the parameters, the conditional probability tables. And we initialize the best net as the original net, the structure with its probability tables. learn the parameters. Actually, here is the step where we learn the probability tables. And then we keep repeating, randomly choosing a pair of nodes, any1 and any2, from the original network. And we do not work successfully changing the original network and then changing again. All of the changes that we do are on the original network itself. We don't change the original network. We just do one modification of the original network and then choose the original network again to do another modification in order to keep the structure, the basic structure of the experts as close as possible to their mental model of the relation between the variables, right? So we choose 2 nodes and then randomly choose to revert or to remove a node between these 2 nodes. If there is no edge between these 2 nodes, we choose an add operation and randomly choose the edge direction because the graph needs to be directed. So this algorithm is very simple, nothing complicated, nothing new here actually, because lots of people implement things like this. I think the detail here that makes this subtly different from other models is that we are always working on the original network. We don't change the network and work on the changed network. Okay, so this is the difference. So we tested that for prostate cancer, breast cancer 1 and breast cancer 2. These are 2 different things here in this example. We have cases of biopsies that were not conclusive, and all of the women that were here were sent to surgery for excision. And the second one was for predicting benign and malignant cases, not biopsies, but mammograms. And this one consisted of mammograms and biopsies that were not conclusive. And the first one, sorry, is a prostate cancer. This network here, the prostate cancer network, the structure, was built by a medical doctor from a hospital in Chaves, I think, because Ana Sarabando was working in a hospital there, and she helped him to build the Bayesian network for the prostate cancer data that they had. And we got data from the literature, actually. We got data from the literature, and we used only the variables that were included in this model that was built by the doctor and with the nurse. This one and these 2 here were built by a medical doctor, specialist in X-rays of the breast. She built this Bayesian network. These 2 Bayesian networks based, actually it was just one Bayesian network, just one structure. She built it based on her experience and on some concepts that were associated with the BI-RADS lexicon, that is the breast imaging and the data reporting, breast imaging and data reporting system. So she built it using these 2 experience and the literature. So prostate cancer has these variables here. The target variable is the status, and this is what we want to predict. We want to predict the status of the patients if they are with these variables here with along the time, if they are going. Although we are not using any dynamic Bayesian network here. We are using just the static Bayesian network. We had 351 patients that died and 145 that were alive 5 years after the surgery. For the breast cancer number 1, we had 45 benign cases and 55 malignant cases for the biopsies. Although all of those 100 went to excision, only 55 were malignant. And after they excised and they performed lots of tests and so on, they found out that. And this one is to predict if biopsy was malignant or benign. This has 153 benign cases and 88 malignant cases. And these two are real data. We are working with real data. For the prostate cancer, we're working with some data that is available in the literature. I have the links. I can provide the links for the data later if you want. So I have here some results for the quantitative results for the ExpertBayes. And this is a correctly classified instances accuracy in the test set using 5-fold cross-validation. And this was taken for a threshold of 0.5. I have precision recall curves for this data, but the precision recall curves don't seem to be very good for some points, so that's why I didn't put it here. So, but these are the correctly classified instances for the 5-fold cross-validation, where for prostate cancer and for breast cancer, we have the original network with this accuracy, and we have ExpertBayes with that algorithm where we remove edges and revert edges and remove nodes and so on with this accuracy. And we also compare this with the best network that was built using Weka with K2 and Weka with the 3 augmented network algorithms. So this one allows any number of parents. I think we were just using 10 parents here as default, and Weka 10 uses only 2 parents for each node at most. And ExpertBayes can allow ExpertBayes take the original network that can have any number of parents and then change a little bit and then obtain the results. So this is an example. This is an example of the graph built by the medical doctor and by the nurse. And these are variables from the prostate cancer that were collected by the experts. The data that we used to train this network here was coming from the literature, and we had 74% of correct classified instances. We wrote a paper about that, and in the paper we have the significance levels and everything from these tests. So I can provide the link as well if you want, if you like. And here is the change that improved the results of the ExpertBayes running for a number of iterations. So ExpertBayes decided that actually this network here is exactly the same as this one. The only thing that ExpertBayes did here was to put a link between DBP and the class. So putting a link between DBP, that's diastolic blood pressure, and the class, that was survive or not survive, the accuracy increased to 76%. This other example, this is the network that was built by the K2 in Weka, and this is the results, the network that was built by TAN that had the accuracy of 71%. So TAN only allows 2 parents per node, and K2 generated this network here that is it's naive Bayes, actually. This is a naive Bayes network that was the best that the model could find. So for the breast cancer, we had 49% accuracy for the original network built by the experts. And with ExpertBayes, what did was to revert this edge here, right? So this is it. It reverted the edge to the outcome, and then the accuracy of the classifier increased to 60%. These are the 2 models that were built by Weka. Weka built this the breast cancer. Oh no, this was the other breast cancer 2, sorry. This was the original network that was very complex. And this is the network that was generated by ExpertBayes that added this link here from, I can't read that anyway, but anyway, it's calcification or KDX, that's diagnosis of calcification with some kind of disease that is here in these nodes. But for this model, this was the model that was built by the expert, right? For this model, WECA generated a much simpler model, that's the naive, saying that this model has a much better results for the data that we used with just a naive model. So sometimes when the expert thinks of using Bayesian connections like this one, this came, as I told you, from the experience of the experts and also from the literature. When you, I think I'm talking too much, right? It's already 3 p.m. Anyway, so what happens that the model is very complex to the experts, but the quantitative model is much simpler, right? So this one achieved accuracy of 80% and this one 79%. So this proves that from that data, the data that we used, a much simpler model was more effective than the more complex model. Anyway, so regarding the scalability that I told you, well, all of these can be modeled with this ExpertBayes framework that we implemented. And in order to mitigate the limitations of ExpertBayes, Andrea started then to implement this scalable software. It runs on Linux and Windows, and it's implemented in C++ and use Qt as the user interface for implementing the user interface. Qt is a very flexible graphical interface for lower level graphical interface that implements lots of things that are very useful for interacting with the user. Andrea is doing a very good job in efficiently implementing data structures, coding, and parallelization for these for all of the algorithms, the structural learning, parameter learning, and inference. For the moment, we only have naive Bayes implemented, fully implemented. He's been working on the implementation of the general model. So for the naive Bayes implementation, he tested this C++ implementation with these data sets that he created synthetically from the iris data sets, where he multiplied the number of columns and multiplied the number of rows, and he has file size of this. And then we tested loading the data, learning the structure, learning the parameters, and calculating inference for the naive Bayes. Okay, so for the naive Bayes, these are the characteristics that we used for the increasing the size of the data. Millions of rows, large string for each predicted value. We also played with the names of the variables and the names of the variables, because this is some limitation as well of other models. And here are some preliminary results that we have for the naive Bayes compared with Bayesian learning. And this is time for data loading. For data loading, R takes 10.5 minutes for the first data set, 59.9 seconds for the second one, 23.3 seconds for the third one, 58.7 for the last one, and high performance ExpertBayes with 8 threads can reduce this quite a lot when loading the data. For parameter learning, we have also very good results compared with Bayesian learning R. I just want you to make sure that you know that R implements some of the Bayesian networks algorithms, especially naive Bayes. Some of the algorithms are implemented in C, but some of them are implemented in the interpreter, and the interpreter has an overhead, right? It's not the same thing as implementing C++. So you need to discount the time that the interpreter takes to do all of these things. But anyway, we can do a very good job with ExpertBayes, reducing to seconds something that takes minutes. And to do inference, we can also do much faster inference, and R cannot do inference if you don't use all the classes that you in the test sets that you use it in the training sets. And R takes 4 hours in this data set here, C2, R took 4 hours to do the inference, while ExpertBayes took 324 seconds or 126 seconds using 8 threads. These things here are here because this data set was used only for training. It was not used for testing or inference. Anyway, I think this ends my talk. I just want to say that Bayesian networks are models that can be visualized and taken into account uncertainty, and they can be very useful when you want to visualize the relations among the variables, probabilistic relations. The available implementations are not very flexible from what I know. They miss some interaction, others miss batch execution or proper testing. Some implementations are not scalable. As we saw, we just compared with R, but we have other comparisons with Weka as well and with other algorithms, just that I didn't put everything here. So, and this software can mitigate some of these problems. And I think this is it. Thank you very much. I hope you enjoyed it.